Alrighty, folks. Not exactly sure 100% where we were when we stopped talking, but I'm pretty sure we were right around here and just had started talking about the Richter and Mercalli scales, how one is more descriptive for the average person, and one is much better for the average scientist, and never the twain shall meet. But what you hear about in the news is the Richter scale, and the biggest thing to take out of that is that when they jump from a whole number to a whole number, the decimals, a little bit, but when they jump whole number to whole number, it's a big jump in what they call magnitude. All right, it's like a whole power, bigger. So, excuse me, logarithmic might be a good word for it. So, it's a big difference to be a 3 or a 4 or a 4 or a 5, okay? You could maybe compare it to getting an 80 versus a 90 on a test, and the decimals come in as all those, 83, 85, 86, whatever. So it's a big difference, and it's even more so a difference with the energy released. And as to why they're not similar, I'm not a geophysicist, I apologize, but why 3 times the energy results in only 10 times the effect. But so we focus on the 10 times the effect. Largest earthquakes ever recorded. I do remember talking about this, the Christmas Day tsunami. I remember that horribly in Sumatra. So what really depends on how bad these earthquakes are, okay? Essentially, the easiest way to think about it is how much energy is released. I mean, that's just a direct correlation there. The question is how do you sometimes get more energy than other times? And the easiest way to think about that is how long in between earthquakes. What it boils down to is it's almost better to have frequent smaller earthquakes than it is to have none and then one huge one. Because you can have the same amount of energy building up. It's just how is it released. Okay? And there's a couple things that depend on that, or that are a function of that, I should say, or that is a function of a couple things. Probably the best way to say it. The rock type is number one. Now, we're talking about plates. Plates are deep down. Deep down. These are your cores or roots of the crust. Okay, the lithosphere, even as we called it, but it's got a little bit of a goo underneath the crust. But so we're just going to call it crust for the moment. Just keep it simple. That's igneous rock. All right, and when we say the rock type, the plates are moving, but there's all this material built up on top of those plates. And that's, I think, sort of what they're looking at here. And you could just get into general durability, how much energy these things can hold before they break. And we can make some really basic assumptions that, sedimentary rocks aren't as durable or aren't as strong as, say, igneous rocks or metamorphic rocks. Okay? But truth be told, on top of these, because I've actually sat and thought about this. I do hear the things I say sometimes. I've thought about this, and sorry, I never went into display mode for you guys. There you go. At the very bottom, it's all the same rock. On top of it, you're going to have a mix of everything. But this is what they tell us, okay? And that then we go on to talk about system energy. When I was a teenager, for whatever reason, it was a really cool thing to try and break, like sporks and pencils and stuff like that. Just, I don't know, it was the 80s. We didn't have a whole lot of stuff to do. So I think about like bending a pencil, right? You're bored in class, you're playing with your pencil, and how far can you break it before it actually snaps? Or can you bend it so far and then take the pressure away and it goes back to normal? That's system energy. How much can it absorb before it breaks? That's what I mean by that word. And none of these are fresh breaks, right? When we're talking about the earthquakes, they're all ancient old seams. So again, I think I started with this on our opening slide. Even after all these years, somehow these rocks aren't worn smooth yet. Okay, so we're really just talking about how tied up, how knotted up these things are. You know, sometimes people will ask about you know, if there's a city on top of it. I don't know if anything we could put on top of these rocks would matter. You know, we do say that when we remove rock, it has an effect. So, you know, maybe. Maybe. Well, I'm just thinking of dead weight, you know, dead weight, yeah, you know, if nothing else. But an object at rest remains at rest, but it could, in theory, you know, weight it down. But I'm just, the big thing that comes to mind is say, San Francisco. And I don't know exactly where the plate goes through. But arguably, you've got development on both sides, and, you know. So I try not to overthink this. But for those of you that are engaged and saying, "Wait a minute, that doesn't quite make sense," I'm with you. I see where there's questions to be had. All right, so just keeping it simple. It's the amount of time between the energy releases. Okay. And Siri agrees, apparently. All right, so changing gears a little bit here. We've got a little mishmash. The end of PowerPoints are always a bit of mishmash. The earth cracking open isn't typically what does the damage. Yeah, some stuff in the immediate vicinity may fall into the earth, okay? Some unfortunate person or sheep or wherever the crack happens to be, you know, it could just open up and swallow them, yeah. But that's not typically what we see as the damage from earthquakes. Okay, not even the shaking of the structures. That's a primary. Okay, we talk about this with flooding, with volcanoes. We get the primary and then the secondary sort of effects. The fires are a big one. Oftentimes I show a video. I haven't actually done it in a while. About the great San Francisco earthquake, and 1901 maybe, leveled. Well, the earthquake leveled some of it, and then the people and the fires leveled the rest of it. And 120 some years later, it's still the same problem. Gas lines and water lines we tend to run underground. When you break one of them, you probably break both of them. They couldn't put out any fires. They didn't have helicopters that could come in and dump tarpfuls of water and so on and so forth. They had some pump trucks back then. It was, you know, one of the most advanced fire systems, fire protection systems in the world at the time. But it still just was no match. So fires remain to this day a huge problem. The obvious structural damage, we talked about how when the energy waves, the seismic energy, comes to the surface, it manifests itself both shaking left and right and shaking up and down. Okay, and you know, we're getting really good with engineering. But we can't go and replace every building. They even try to, you know, retrofit some of them in these areas where they're prone to earthquake damage. It's essentially, you know, putting these things on springs sometimes. That's the retrofitting. When we build them fresh and new, I think they've been inducing the ability to sway, which would be scary as hell if you were stuck in it, but still better than collapsing. It's some really, really neat stuff. But we still have the losses. And landslides, something maybe you didn't think of, okay? When you shake like that, any loose material is going to fall. I don't have a slide for it, I don't think, but there's an effect called liquefaction. They actually mentioned it in the video. we saw. Really horrible example of it happened. When was this Alaska one? I don't know if it was. Might have been the 64 quake in Alaska. It was a while ago, but not like ancient. There was these neighborhoods on a sort of a cliffside view kind of place. Nice neighborhood, and the earthquake shook, and it shook so much that liquefaction. There was a layer of sand in there. Either the engineers knew about it, or we didn't know this would happen. Who knows why? But this whole neighborhood was built on this layer of sand, and it turned into basically ball bearings. And the slope of it happened to be towards the cliff, and I guess just everything just rolled off the damn cliff. It was horrible. I don't remember details if people got out, if people didn't get out. I'm sure it was a mix, but liquefaction is certainly an issue. Another effector, and everybody knows, tsunamis. Might not have known how to spell it, but everybody's heard of tsunamis. And the number one thing we want to tell you right now, and they've actually gotten better about this. You guys, the media is getting better when they talk about it. It's not a tidal wave, all right? That's what they always used to call them. They're tidal waves. It's got nothing to do with tides. They are giant waves, don't get me wrong, but not tidal waves. And I don't know that there was ever a tidal wave, right? But the tides are one thing. This is probably always what they meant. It was just sort of a misnomer, if you would. The thing about tsunamis is they don't really show up, so to speak, until the water starts to get really shallow. There's so many cases of boats out to sea that it just felt like a swell to them. All right, but there's a lot going on. The folks in front of me here, they're gonna see my fingers twirling around each other like a barrel. There's these wave forms, they call them basically. If you can picture, if you've been lucky enough to get to a beach, as that wave is rolling in, there's several sort of tumbling systems in there. Bigger ones make bigger ones. The water overturning, just little convection cells, if you would. All right. With these tsunamis, the energy released pushes the water, and it starts this swell. But it's not until those waveforms hit the floor of the ocean that it starts to cascade and tumble. All right, so it just sort of swells through. But then once those waveforms start collapsing, it builds and builds and builds and builds and builds. There's tons of footage out there. Nothing's happened real frequently, so you guys might have missed it. But in classes past 5-10 years ago, there was some, tsunami accounts here and there, especially with the advent of video cameras everywhere. There was a famous one somewhere on the southeast coast of Asia, some touristy destination there, and the hotel camera caught everything. If you're familiar with tides, again, the tide goes out, the tide comes in. Well, the tide kept going out and out and out and out. And silly people that we are, I probably would have wandered out too, don't get me wrong. But people kept wandering out there going, oh, wow, look, where's all the water going? And then it just started coming back. And it came back, and it came back, and it went past their lawn chairs. It went past the fancy fence and all that was separating the hotel from the beach, and then it went through the hotel, and it just kept coming. Crazy thing about that is, they say no animals were harmed, lost, etc. It was only the people that were killed, and this is sort of foreshadowing to a slide or two that's coming up. Critters got the heck out of the way. All right, it's just these silly people that didn't run away. These can also happen with asteroid impacts. If you studied the demise of the dinosaurs, you got the Chicxulub crater, the Chicken Club crater as I call it, and among the various lines of evidence that they found with this thing. One of them is tsunami deposits. And this thing hit in the Gulf of Mexico. I want to say they found tsunami deposits as far north as Wisconsin. It was insane. It was huge. Imagine, dropping a bowling ball in your swimming pool kind of thing, but times a gajillion. So, asteroid impacts are another way that we do get tsunamis. Well, hopefully none of those, but coming soon. But certainly we still see them from earthquake energy released underwater. All right, I don't know if I actually spelled out that bullet to you. You all been staring at it for 5 minutes, but we're releasing that seismic energy underwater. Okay. So, speaking of animals running away, this is tough. Long term, they really don't have a whole lot to go on. Believe me, they're studying. There's places, again, over on the east coast of Asia, the Pacific Islands over there. This is a huge, huge deal. California, it's a huge deal, but I don't want to say it's one state, but it's a lot smaller impact area. And there's certainly other places, don't get me wrong. But these folks are working on it. And the problem is that you may have heard of force, you've heard of aftershocks, right? Well, there's foreshocks as well. And foreshocks don't always lead to something. The bigger problem is doing something about it. So even if we came up with a correlation, right? When we see foreshocks of this level on the Richter, 70% of the time it results in an earthquake happening. Well, then you go to the mayor with that, or the governor, or whomever, and they're like, 70%, huh? So not always? What are they worried about? Well, they're worrying about mass panic. They're worried about evacuating a city and this and that and the other thing. So let's say they listen to the geologist the first time and it doesn't happen. And even with people, think about this with hurricane evacuations and stuff. People now, they decide to stay, or some of them just get the heck out no matter what. But you see, oh, maybe it's not going to be that bad, I'll stay. It compounds. And it is a lot to evacuate. Okay, I can't speak for the towns over in Asia, but, speaking for America here, to evacuate L.A. or San Francisco. Where are they going to go, first of all? The bridges and all. It's just... So they don't have anything solid, and what ideas they do have don't always work out. Short term, we're pretty great, but again, what are you going to do short term? You sure as heck, again, aren't going to evacuate San Francisco in 2 hours. So we see the foreshocks that I talked about. We see changes in the land surface. Oftentimes they'll report after the fact, they'll report some bulging happens, okay? The best one, the most consistent one, is animal behavior. But again, they don't have ESP, okay? They're responding to subtler things that we're no longer, attuned to, from the soles in our shoes and the concrete under our feet and so on and so forth. We're animals as well. Arguably, we should have these abilities. But, monitoring the animal behaviors doesn't exactly apply in this situation, but if I could give you one bit of advice through this entire semester, is if you're walking down the street heading into the woods and you see all of the animals running out of the woods, don't go into the woods. Okay? Same idea. But so there's not a whole heck of a lot we can do at any rate. But they are monitoring every moment of every day and going through the data. We do know that earthquakes tend to happen in certain places over and over again. But we also know that You know, sometimes we just get them in random places, like upstate New York. All right, so I mentioned that we had a really cool lab that we will do at some point. And we've been talking about seismographs. A couple times that word has come up. So how do we actually use a seismograph to locate an earthquake? Well, seismographs record distance. An earthquake happened within 300 miles of here. So that's really great for drawing a circle. You draw a circle with a 300-mile radius. You get a 600-mile diameter. And all right, we narrowed this down to a 300-mile radius. Well, luckily, there's other seismograph stations out and about. So you get the next closest one and the next closest one. In fact, they prefer to use 3. It's called triangulation. They use it on cell phone towers, or at least they used to. I'm not sure if it's still a practice. You got a lost hiker or whatever, you know, where's the last time their phone pinged a tower? They record all that crap. Okay, but again, that just gives you a radius, so you got to find another tower and another tower. And ideally, those circles we talk about overlap in one point, or at least a much smaller area than a 300-mile radius. It's not that hard to use these. As I said, we're going to run a lab on it. We talked about the P wave and the S wave, okay, as the 2 hits that a seismograph gets. You simply measure the time lapse between the P and the S wave, and you use that onto another table that they've made for you. That's I think it's called the travel time table. I always call it a time travel table, but whatever. You pour it up on this thing, and it gives you a distance. Okay. And again, that's assuming on the rock material and so on and so forth. Then we have also we care about the peak, the height of the waves. I strangely don't have a seismograph reader. I don't know why I don't have a picture of a seismograph. I'm going to add one real quick, because that should totally be here.
Seismic wave, right? Seismic wave, right?
Well, I can't get a picture of a seismic wave, but I can get a picture of a seismogram. If I can spell it right. Phooey fudge. So you guys have seen those, like I said, in movies and everything. Let me steal it. This is Wikipedia. Okay, good. So Wiki Commons is fair game. And I don't like that one. Cooney. I don't want to borrow from Cooney. Stock photos. Here we go. Okay, boom. Boom. No. Really? It's a tiny little picture. So we've got this roll of paper that's continually moving. There's a little pen bouncing on it that you can't quite see in here. So the seismograph is the machine. Seismogram is the piece of paper, all right, that it produces. Beautiful. And one more thing here. Insert text. Boom, boom, boom. All right, so that makes that. Then this here is, sorry, I found it's best to get rid of these silly little boxes. There we go. That creates this. And so we're looking at two things here. We're looking at the distance between when this hits and when that hits. And then we're also looking at what they call the amplitude, the highest wave that it actually hits. Bam. All right, don't have to cite that one. It's got the cite built in. So here's your P wave, here's your S wave. Then they take that information, again, the lag between here and here, and you'll be doing this in lab, and they plot it on this table, and they come up with a distance in kilometers. I mentioned 3 seismographs and circles overlapping. All right, and boom, boom, boom. The idea is your earthquake is right there. It's very simple. And not too horribly long ago, we had to do that with GPSs when they were still worried about people strapping them onto the tip of a missile and so on and so forth. They had a disruption algorithm in the GPS frequency. And it was more like, instead of 3 meters, it was more like 10 meters or something like that. Not that you still can't decimate a city with that, but it was enough to be not specific. And so they taught us again back, it was early 90s, I guess, how to use, 3 different GPSs to figure out where you actually were. Suffice it to say, it made it difficult to use them for most things back then. I do remember having, the small handhelds like we used in lab on a little suction cup in my car window, but the 1.5 by 2.5 inch screen wasn't really great. But, it wasn't much long after that they, I'd say by the mid-90s, they got rid of the scrambler. And then they just started growing from there. You guys may have grown up with TomToms or Garmins or whatever strapped your folks had in their windshields. And nowadays, of course, our phones do all of that. So, and they have their own issues to scramble things up. This is really outdated. We don't have a whole lot of earthquakes on the East Coast. And we've probably had a couple since I wrote this, and I didn't bother recording them. I still do remember my one buddy posted a picture of, you kids these days call it a meme, I think. I know what a meme is, but posted a picture of a lawn chair tipped over, and it said, "Oh, the humanity." This earthquake that hit the D.C., Virginia area. For them, it was, kind of scary, I suppose, because things don't usually shake over there. But compared to other earthquakes, it was not a whole lot. There was one in Albany, very close to it. I don't want to say that I believe in the butterfly effect or something, along those lines. I don't not believe in it either. But to see these, when you see an earthquake on one part of a plate, that you don't see a repercussion somewhere else. And I do remember asking my geophysics teacher at the time, no. But that was, 30 years ago. Who knows, what we've learned nowadays. But these seem, close enough for something. But even on the Pacific plate, if you guys pay attention to it, If you'll see something rumble over in Japan, well, then we're going to see something rumble over in, Washington or something, California, and vice versa. Huh?
That's right, because the West Coast.
Yeah, it's all one big hunk of rock between West Coast of U.S. and the East Coast of Asia. You get a little farther south, it's a bunch of tiny little plates. Don't get me wrong. Where the Pacific Islands are, it is a jumbled mess. But for the first top half of the Pacific plate, it's fairly solid there. But these aftershocks, these are good size. These are good size things. Aftershocks can sometimes be bigger than the earthquake. I always wonder why they don't reclassify them. But that was not my purview. And as I mentioned, we do see earthquakes, I don't want to say with some frequency, but it's not uncommon up on the New York-Canada border, up in Messina and whatnot. They do, Potsdam, they do tend to have. In fact, I'd be willing to bet Potsdam has a seismograph, but they do happen up there. So this is more to my online folks than anybody else. They have a project you guys don't have, since they don't have to put up with me in person. We have it as a natural disaster map, and I tried over the years to come up with a better name than that. But the idea is that whether you're taking earth science with me or geology from me, that I've tried, and I think you guys get this as well, I try to get across to you that this is a current events kind of science, okay? Yeah, in biology or chemistry, you might hear a breakthrough here or there about something cancer research or this, that, or the other thing. But earth science, it's studying Mother Nature, and she is constantly giving us things to look at. Wildfires in Jersey right now, for example, in Pennsylvania, crying out loud. But so they keep track of them over the semester just to see that they're being surrounded by this class. But I always warn them, I say, you got to keep up on this. You guys at home, it's a little late for this morning, but you got to keep up on this because you can't do it all in the last week of classes. And most of them don't listen to me. So what this is, and it's kind of hard to tell, but you see all this tiny little, let me go back into mode here. It's still not that big, but where's my mouse? I don't even see my mouse. There's my mouse. All those tiny little dots there, all those tiny little dots in there, all right? And that's just in the U.S. That's how many earthquakes there are in that 1 week, all right? So they're always happening. They're just not happening usually somewhere where the media and or us care about. So you don't hear about them. And back to the point of the project they're supposed to be working on, if you go at the end of the semester and try to find earthquakes that happened during the semester, you're going to find about 300 or 3,000 or whatever. Impossible to map. So they're always happening. We get the impression that these are rare things. Thank goodness in places, again, that we care about, for lack of a less callous word, they're rare. Okay, they're not frequent at any rate, but they're constantly happening out in the Aleutian Islands, and the media doesn't care about that, so you don't hear about that, so on and so forth. All right, so that wraps up earthquakes. And please read the earthquake chapter. A lot of neat stuff in there. Goodbye.